Assalamu alaikum. Waiting for people to join. I hope student leaders ने strike की call नहीं दी हुई. So, okay, good. And I am in EME college. So, in my office. So, doing it from the office. So, I want to first recap what we did last time. And last time we started studying about the linear phase FIR filter. Linear phase FIR filters. And because IR filter has this problem of non-constant group delay, means their phase is not linear. So we want to make sure that the filter we design should have a constant group delay. A constant group delay means it should have its phase should be minus alpha omega and maybe another factor beta, so that once you take its derivative, which is the group delay, so it comes out to be a constant. Negative derivative of the phase is group delay. So we have studied this. Very easy to achieve it, and that once you design the impulse response, it should be either symmetric or anti-symmetric. So it's easy. So whenever you see an FIR filter, and you must have designed many, and you will find out that mostly they are symmetric filter. And what is symmetry? Like first coefficient is same as the last, second is same as second last. So they may be, this is called M. This M could be even or M could be odd. If M is odd, then it'll be something like this. Okay, so this is M is odd and M is even. So and then it is symmetric or it is asymmetric. And then in last time, once my camera was facing somewhere else, and then I also uploaded a 9 to 10 minutes video. This is the relationship. The symmetry, the consequence of symmetry is that h of z has a relationship with h of z inverse. How to get h of z inverse? Replace z by z inverse in the z transform. And we saw that this is an interesting relationship. And because of this relationship, we know that if h of z is 0, then this is also going to be 0. H of z inverse is also going to be 0. So z naught is a 0, then 1 over z naught is also a 0 of the system. And I have also posted a question which I gave to degree 28 electrical engineering, and for some reason all their questions were very difficult to solve questions, and I have also challenged you to solve it, find out an h of n, knowing one, finding out the 7 coefficients, only knowing this little information. And we know that so we know that if it is a 0 at z naught, this is our z naught, r exponential. So 1, or this is, we have done this last time, 1 over z naught is equal to 1 over r exponential j theta, 1 over r exponential minus j theta. So means that 1 over r, usually it is less than 1. Let's say if it is 0.5, so it is 1 over 0.5, which is 2. So you will have a 0 here. And theta is minus. So you have another 0 here. Okay, this is at 1 over r. And we know if it is real, then it is going to have a 0 here also. Complex conjugate pair. So this must also have a complex conjugate pair, so it is going to be here. So knowing 1, you know 4. Rest of the 3. So they will always exist. Today I'll show you in MATLAB as well. Interesting patterns that they exist in clusters of 4, the zeros of a linear phase FIR filter. Obviously, if you have a 0 on the unit circle, then 1 over 1 is also 1, so you will not have another here, but you will still have its complex conjugate pair. So if there are zeros, if they are existing on the unit circle, in that case, you will only have a complex conjugate pair, not 4 in a cluster, So knowing this, the linear phase FIR filters are divided into 4 types. These are the 4 types. It may be symmetric. Symmetric, we know that for every coefficient, you have this copy of the coefficient. The first and the last and the second last. The second is if you have this M is even, like this is an even, so this is type 1 filter. And we will find out why we are saying type 1, type 2, type 3, type 4. So type 1 is symmetric and M is even. Type 2 is symmetric and M is odd. Type 3 is anti-symmetric and M is even. So you can always draw this like this, then you have an inverse here. If you have this, you have an inverse here and 0 here. So 0, 1, 2, 3, 4. So this is a type 3 filter. And type 4 is M is odd. So M is odd is, I've drawn it here, but this, then you have this. So 0, 1, 2, 3. So M is odd. So these are the 4 types: type 1, type 2, type 3, type 4. Now a good question is why they are being classified into 4 different types. And the reason is this relationship. This relationship is for type 1 and type 2, and there will be a negative sign because of this negative sign. So let's now closely observe these 2 relationships for type 1 and type 2. Your h of z is equal to z minus m. Okay. Type 1 is okay. Type 1 has no other constraint except that a 0 at z naught. There will be a 0 at 1 over z naught. But type 2 is interesting. What is the value of the transfer function at minus 1? Okay, and you say, okay, put minus 1 here, minus 1. And remember, this is M is odd. Odd means, let's say it is 3 or 5, or let's say it is 5. Or h of z inverse 1 over minus 1 is 1 over minus 1. So because of this odd, we know the minus 1. So h of minus 1 is equal to minus h of minus 1. And this is an inconsistent mathematical expression saying x is equal to minus x. Okay, 1 is equal to minus 1, 2 is equal to minus 2, and this is not possible. This is only possible, so this is an inconsistent mathematical expression saying something is equal to its negative. It cannot happen except at 0. Except at 0. Okay, so it means that the type 2, and this is important, the type 2 filter got to have a 0 at minus 1. What is minus 1? So if I draw it here, and I plot with the red color, the unit circle is the important circle. We have been talking about this a lot. So there has to be a 0 at here, at minus 1. This is minus 1. Has to be a 0 here. Rest is fine. They will occur in group of 4 and all of that zeros. But type 2, because to resolve this inconsistency in this expression, it has got to have a 0 here. So this is for the type 2 filter. What if a 0 here means that it will not, a type 2 filter will not let pass the pi frequency, the highest frequency. So once you plot its Fourier transform, the type 2 filter, it will come down to 0 at pi. Guaranteed. It's Fourier transform because we know once you place a 0 on the unit circle, so it touches down, the frequency response touches down to 0. Means you cannot have a high pass filter. High pass filter is a filter which let pass pi frequency. This is a high pass filter. So no high pass filter possible for M is odd, which is type 2. So this is a very important relationship, and that's why there are 4 different types. Once I'll show you in a while on MATLAB. Then once you design a filter, an FIR filter in MATLAB, and you say automatically select the length of the filter, just minimum length, whatever it is. So if it is a high pass filter, MATLAB will never select an M which is odd, because you cannot have an high pass filter once M is odd. Okay, so M got to be even. The length, if you force MATLAB, I don't know, will it disobey or do something? So type 3 and type 4 FIR filters. Type 3 and 4 are anti-symmetric, means h of z is minus z minus m, h of z minus 1. Okay, so this is type 3. Type 3 is M is even, type 4 M is odd, and that is everywhere. Z naught and 1 over z naught, that is for all the 4 cases. But now here is another interesting mathematical inconsistency in type 3 filters, and these are anti-symmetric, and I hope you understand. Means you have these type of response, impulse response, which is anti-symmetric. 0, 1, 2, 3, 4. So 4, it is type 3 filter. Okay, usually type 3 has a 0 in between. So for this inconsistency is, what if z is equal to 1? So h of 1 is equal to minus z something even, let's say 4. H of 1 over 1 is 1. So the same problem. Even so, either here also, because z is 1 raised to the power minus 4 is going to be 1. So it becomes h of 1 is equal to minus h of 1. Inconsistent. This is not possible. This is only possible if you have a 0 here. So what does it mean? That if you draw it, the same thing, it has to be a 0. If I draw a unit circle, okay, there has to be a 0 here. Means you cannot have a low pass filter as type 3 filter. Not possible, because it will not let the 0 frequency, the DC value, to pass, and low pass filter has to be like this. Okay, so but it will not let, it will make it jump to 0, this frequency, 0 frequency will not let the 0 frequency pass. Rest is the same, like occurring in 4. So type 3 filter cannot be low pass, not possible. Then there is another problem. What is at minus 1? Minus 1 minus minus 1 raised to the power something which is even, h of minus 1, you know, minus 1, so it'll make negative positive. So this is also problematic. This is an inconsistency, it has to be 0. It means there has to be a 0 here as well. So type 3 filter can neither be a low pass or a high pass filter. Type 3 filter can never be a low pass and a high pass filter, and so this is problematic. Okay, so I'll leave the fourth one to you, where it is odd. Obviously this will not be a problem. Once it is an odd, it will make this consistent, but this will be a problem. So type 4 filter, you cannot have a low pass filter. So once you put all these together, so type 1, type 2, type 3, type 4, there is no problem. You can have all kinds of filter as type 1, because as a consequence of symmetry, it does not place a 0, force a 0 somewhere. But type 2, it forces a 0 here, so no high pass not possible. Type 3, it puts 2 0 here and here. So type 1 does not put, but only a pair. Every 0 here, you have a 0 here, which is for every case, and we don't worry about that. So this low pass not possible, high pass not possible, and type 4 is low pass not possible. Okay, so these are the 4 different types of filters, and that's why the type is important: type 1, type 2, type 3, and type 4. So let me show you this in MATLAB as well. For example, this, as you can easily guess, this is M is order 7. M is 7. So if you look at the pole 0 plot, 7 is type 2, and type 2, as you can easily see, that there is a 0 here. So this cannot be a high pass, so I have designed actually a band pass filter. So now let's start seeing this interesting, and you play with this, and I hope we'll design a lab where you can just have fun with. So design a low pass filter with minimum order. Look, see, you see, it's beautiful patterns. A cluster of 4, a 0 here, a 0 here, a 0 here, a 0 here. So for every 0, you see 4 zeros. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3. So they exist in clusters of 4. This is a frequency you are going to pass, and the zeros are placed. The filter design package has placed zeros on the unit circle. So M is 45, a 0 is placed on pi as well. Okay. So if you design a high pass, you see the location of zeros have changed. Now those zeros, the cluster of 4s are on the high pass spectrum, and the zeros are placed on the unit circle, and they will not let this frequency to pass. If you go and look at the magnitude of the frequency response, you will be able to understand. So the zeros here will make the frequency go 0, 0, 0, 0, 0, and let pass these frequencies, which are the high frequencies. Okay. So similarly, you can design a band pass. Band pass, as you know, if you design. So now if I ask you a question, that how do you think that your zeros will be placed on the unit circle? This is from 0 to pi, okay, and we know that from 0 to minus pi is going to repeat itself. And I can tell you there will be zeros on the unit circle from here to here, and then there will be cluster of 4s in this region, and then there will again be zeros placed on the unit circle. So this is my guess, and if you look at this, you say, wow, this is actually true. Okay, we can perhaps specify the order to reduce the size and see it more clearly. Let's say order 10 or something like that. So this is how you are going to see the filter. Or if you say minimum order and change these specs to a little 40 dB, let's say, and change this to just relaxing the attenuation to make sure that you have. So this is the filter. These are clusters of 4, the band which you are going to pass, and the band you are going to stop will place zeros on the unit circle. So you can play with this at your own and see. And if you are designing an IIR filter, okay, this is also important. And I hope that you have already seen this, but let me just show you the IIR filter and minimum order and your design filter. And now there are poles, and the frequencies which you want to let pass, it will place poles there, and the frequency you intend to stop, it will place zeros on the unit circle. So the poles are placed. If I design, for example, a low pass filter, okay, so what do we expect to have? I expect that all the poles will be in the lower frequencies. These are the poles, low frequency, and zeros are where we have high frequencies. And because it's 40 dB, if you increase the dB, which is the attenuation, you are making a filter to have a more stringent constraint. So with more stringent constraint, obviously the order will increase, and you are going to see more poles and more zeros being placed. The order is increased to 8. So this is important, that just by looking at the pole zeros, we can guess about whether the filter is a low pass or a high pass or a band pass. For example, if I do a band pass, what do you expect to have? Where should you see the poles? So okay, let's look at the band pass. Band pass filter design, and precisely this is what I was expecting. The frequency which I want to let pass, there are poles, and frequency which I want to stop, there are zeros on the unit circle. What about high pass and band stop? This is interesting. Band stop, you are stopping a band to pass. Obviously the band you intend to stop will have zeros, and the band which you want to let pass, there will be poles. So zeros are placed on the unit circle to stop frequencies, and in IIR filter there are poles in complex conjugate pairs, the frequency which you want to pass. And in linear phase FIR filter, there are clusters of 4 zeros in the frequencies which you want to let pass. There exist clusters of zeros, and that we have seen in the MATLAB toolbox and as well as in theory as well. So with this play with the MATLAB, we are almost done with this chapter, which is the linear phase FIR filters. So one way of looking at the filters is what we have seen here, and then there is yet another way, and that is to put the frequency response in the format that we want to see. And what is that format? The format is h exponential j omega magnitude exponential minus j alpha omega minus j alpha omega plus beta. Okay, this is the format of a linear phase FIR filter. For example, if I ask you to find out, this is a filter 1, 2, 3, 4. This is a filter 0, 1, 2, 3, 4. Okay, and I can ask you a question. Obviously, is this which type of linear phase FIR filter it is, and obviously you can just give an answer that what cluster of 4 zeros play in the frequency we want to pass. The frequencies you want to pass, cluster of zeros will let those frequencies pass. Okay, and we are not ourselves placing them. The MATLAB toolbox is placing the clusters of zeros in those frequencies which we want to pass. Okay, so and the poles or the zeros on the unit circle will not let frequencies pass. So by just looking at the linear phase FIR filter plot, we can tell about that what is actually happening there. So so this is type 1 linear phase FIR filter. If I ask you to convert it, put it in this form, and you say, oh, no problem, I can put it in this form, and for that you take its Fourier transform, and you know the Fourier transform is h exponential j omega. N goes from 0 to 4, everywhere it is 1, 1, 1, 1, and exponential minus j omega n. This is a formula for finding the Fourier transform. And then, because it is, the formula is like n is equal to 0 to 4 exponential minus j omega raised to the power n. And we know that if this is the formula, alpha raised to the power n. So its answer is 1 minus alpha raised to the power n plus 1, which will be exponential minus j omega 5 divided by 1 minus exponential minus j omega. Okay, just simply the formula which says alpha raised to the power n summation is n goes from 0 to, or k goes from 0 to n. It is alpha of k is 1 minus alpha n plus 1 over 1 minus alpha. So we know this relationship. Okay, this relationship can be put into a better form by keeping this 1 as exponential minus j omega 5 exponential plus j omega 5 minus exponential minus j omega 5. 1 can be written as this. This is a trick we play a lot in signal processing. Okay, just remember this by heart. That 1 can be replaced with a negative positive. As you add, you get a 1. But by doing this, you are helping this expression to be reduced into a better format. So it's a trick which is a very common trick in signal processing. So this minus minus, you take this common, exponential minus j omega 5, and rest is what is left is a sign 2j sine 5 omega. Similarly, you take exponential minus j omega, exponential minus j omega, and left is this is 5 divided by divided by 2. This is exponential minus j omega 5 divided by 2, 5 divided by 2, 5 divided by 2, omega over 2, omega over 2, omega over 2 minus j omega over 2. So this is a trick. Minus plus here, and here the 1 omega 5 is split into 2 5 by 2 5 by 2, and you are taking 5 by 2 as common, and you are getting 5 by 2 here. So omega this common, and you are getting 2j sine omega over 2 common. Okay, so 2j cancels with 2j, and this expression is sine 5 omega over 2 divided by sine omega over 2. This is the real part, and the left is exponential minus j omega 5, or omega this will be omega of 2, and it is in that format. H exponential j omega is the magnitude and exponential minus j omega alpha is the phase. So alpha is equal to 2, beta is equal to 0. Okay. So this is yet another interpretation of linear phase FIR filter, that all linear phase FIR filters can be brought to this form. All real magnitude and a phase which has an alpha of omega plus beta, maybe a maximum. So this is one interpretation. The other, I have told you that there are clusters of zeros that you see in this. So with this, we are actually done with this chapter, except one thing is left, and I should also cover that. It is all pass, because somebody also asked me that if IIR filter gives you a non-uniform phase or non-linear group delay, then why to use it? Okay, and what to do to basically fix the phase. To fix the phase, we use phase compensators, something which will just change the phase of the IIR filters. We put another filter. So this is how it is done. There is an IIR filter, and you say, oh, it has corrupted my phase, I don't want either. I should have used a linear phase FIR filter. No problem. You use another phase, which is a phase compensator, which is an all pass filter. All pass means it will not corrupt your frequencies. Its frequency response, magnitude of the frequency response will be 1 everywhere. So means once you have filtered the unwanted frequency here, it will no more filter out any frequencies. It will only correct the phases, bring the phases back to their original positions, so that all the frequencies in the signal are delayed by the same amount. So this is the job of an IR, all pass filter, as a phase compensator. So impulse response of an this is called all pass filter. They seem useless, right? They sound useless. They are not going to change the frequency constants. What is the use of these filters? So use of these filters is as phase compensator. So for every zero there is a balancing pole. So it says if it has a pole at A, then it has a 0 at 1 over A magnitude, to make sure that it is basically cancelling the effect of a pole to filter out the magnitudes of the frequencies. And then it has even higher order form as well. So this brings us to end of the subject, this chapter. And remember, we have learned a very interesting aspect of filters, and that is phase. That we need to worry about the phases of different frequencies in our signal. And phases of different frequencies basically is the shape of the signal. And shape of the signal of different frequency contents. Your signal usually has different frequency contents, and once we are filtering out things, we don't want their relative position of these frequencies to change, because if the relative position of these frequencies changes, it'll change the shape of the signal, which usually we don't like in many applications. And so you either use an IR filter which keeps this thing in mind, that the frequencies which you're going to pass, it must not distort their phases, or you use a phase compensator, or you use an FIR, linear phase FIR filter. So it is your choice that which filter you use, but you must always plot the overall phase response or the group delay to get this comfort that your signal processing is not going to corrupt the shape of the signal. So, and this is an important topic. Usually people don't worry about phases, but we need to worry about the phases. Next, which Dr. Ali has already started, the chapter is about implementation. So signal processing is about three things. It's a triangle. Okay. Once you are learning signal processing, there are three things which you need to learn. One is the analysis. How do you analyze? So we have, up till now, we have only learned analysis, almost. The frequency response, phase response, Z transform, okay, or representation. So we have learned representation and analysis, how you represent a signal, how do you take its DTFT, how you take its Z transform, what are the poles and zeros, why should they be inside the unit circle. So we have focused on the analysis part. Yet we have to cover 3 different aspects of signal processing. The second is the implementation part. How do you implement a signal processing system in C or an FPGA or a digital signal processor? Dr. Ali has already given you an intro that implementing a signal processing system on a digital signal processor. Okay. The third is the design part, which we will cover in the last, because this is the toughest, the difficult part, that how you actually design these systems. So these are the 3 different aspects. Up till now we have only covered the analysis part, and Dr. Ali has started you to learn about the implementation part. And interestingly, why to study implementation? I know convolution summation, I know difference equation, and these are the only 2 things that you are going to implement. So implementation, understanding the implementation is not difficult. Okay, why? Because from the implementation perspective, you only need to worry about 2 set of equations. One is a convolution for implementation, you only need to worry about 2 equations in signal processing. Convolution summation, which says y of n is summation k goes from 0 to L minus 1 h of k. So we have seen this equation so many times. What is difficult in, and obviously a question comes to our mind, what is difficult in implementing? I am a coder, I just open this up, okay, and it'll take me 5 minutes. If I'm a good programmer, it'll not take me more than 5 minutes to implement this equation, not more than 5 minutes, or I may keep debugging it, but basic code I can write, because the number of programs I have written, this is just piece of cake. And the second one is y of n is equal to minus summation k goes from 1 to n a of k y of n minus k plus summation k goes from 0 to m b of k to xn minus k. Again, if you are a programmer, okay, and you say this, I can just implement it, so simple, I can just in 5 to 10 minutes I can implement, a program which can implement this. How? Let's say it's a second order, for example. You say, okay, this is a typical example, y of n is 0.5 y of n minus 1 plus 0.6 y of n minus 2 plus 2 x of n plus 0.6 x of n minus 1. Not knowing anything, okay? Not even knowing signal processing. Not knowing signal processing. Writing this code is very trivial. That you get an x of n, okay? You get an x of n. You say, okay, input. So you define a variable input. You say, okay, input, I get an input, and you have a previous input, and then you have a current output, then you have a previous output. A dumb programmer would implement it like this: previous to previous output. Okay, so these, you have the new input comes in here, so a function calls input comes in here. You have already placed the previous input into the previous input. You have the you need to compute the current output. You already have this and this in place. So you write the equation: current out is equal to 0.5 into previous out plus 0.6 into, okay, a very dumb programmer will take 5 minutes. Previous out plus 2 into input plus 0.6 into previous input. And you see I'm done. All now I have to do is this input goes to previous input, the current output goes to previous output, and previous to previous output goes to previous output, and you are done. Okay, and you are done. So any programmer can easily as a matter of fact, the first job I did while I was at tech, there was a very good C programmer. I may have his code still, perhaps. I learned a lot from his programming skills, but he was implementing a signal processing system. I mean, he had absolutely no idea about signal processing. He was making a telephone exchange with just the DTMF detection using a difference equation like this. And he almost did something like this, and a long piece of code which he wrote, and the exchange could only process like 5 calls, and they wanted to do 64 calls. And then I changed the code to make sure, knowing the DSP helped me to basically optimize it, and the same exchange could do hundreds of calls. So obviously it matters that you know that what are the different ways of implementing a signal processing system. So now if you try to make a flow diagram, which Dr. Ali has been making it for you, and I perhaps need not to repeat it, but I know Dr. Ali has shown you this, that okay, this is y of n which you intend to compute, this is y of n minus 1, and this is y of n minus 2 here, and here you multiply it with a1, and here you multiply it with minus a2, and then you add and add. Okay, and then you have this x of n, you put a delay here, so you get here x of n minus 1, you have another delay here, or a variable storage, here you have x of n minus 2. So you do a multiply here, which is b of 1, you have a multiply here, which is b of 2, you add, and you add. And you can directly convert this in, if you have an FPGA, so you use 1, 2, 3, 4 multipliers and 1, 2, 3, 4 adders to implement this. Or if you are a C coder, I have already shown you the code, and you may want to keep these in a buffer if it is a longer filter, but this is an implementation which you implemented by looking at the difference equation. And now you will be surprised, honestly, and it's mind-boggling that people are still doing their PhDs, okay, in exploring different implementation of this so stupid and simple architect. PhDs, I'm talking about PhDs, okay? They're doing the PhDs, and because this is all signal processing is doing, it's just implementing FIR filters, IR filters, but their length and a very, very high speed, because if it is a 5G modem, and 5G modem has to give you 10 gigabit per second. So just imagine 10 gigabit per second, okay? So all the filtering must be happening, the data which you have to basically process must be even at a higher rate, and you are passing it through filters, you are passing it through, these type of things, and passing those filters at this rate. Yesterday actually I received a message from Shehbaz, who was our graduate, and then he was so good in FPGA design, he worked for CARE, and now he got a position as an assistant professor. He joined Purdue University, and he was even called in Stanford University. He spent a lot of time in Stanford, and this was his basically area of interest, that he could take an algorithm and map it on FPGAs, and he actually asked if somebody is interested in getting his PhD with him at Purdue, so he could able to fund as well. So this is what the Shehbaz and many graduates from our department, they got mastery in actually in implementing high speed, very high speed, and they are working in companies who are actually developing these days. Many of our graduates are working in companies, and what they are doing, they are making interesting architecture to process data at very high rate, like 10 gigabits, 20 gigabits. Okay, so implementation is very exciting and very challenging. It's not simple like this. So the first variation in this implementation comes from somebody thinking about this and thinking this not as two systems, as one system, rather two systems. He said, oh, this is my one system, and this is my second system. Okay, somebody thinking, like this. So why should I think this as two system? Why should not I think this as my two system, and why should not I tear this? Sorry of tearing the paper. And because these are linear, why not to place them like this? Okay, why not place them like this? Because if they are linear, they can be placed like this, that you can cut them and you can put them in different orders. So why should you do this? A question, why should you do this? Interesting. If you do this, then you find out that it is the same value which you are storing in this register and this register. It is the same value which you are storing in this register and this register. So you can reduce the number of registers, the number of storage element. And this is what takes the power, this takes the area, because registers takes the power once at every clock. So this was the first approach of in the design, and this is called direct form 2. So in direct form 2, the filter is broken into cut into two and implemented like this. And so then you have, as you can see from here, you implement this part first and this part second. So if I draw this here, let me draw this so that you get better visualization of what is happening. Looking at the tone paper, I am just redrawing so that why you can do this, because linear system you can implement them in any order, and one second order or one IR filter is basically two system. One is feed forward path and the feed reverse path. So this is the filter. You put an XFN here, you get a YFN here, and then you just realize that here you are wasting storage because this is same as this is same as this. So why not to collapse them and make it into a filter like this. In my digital system design book, I have now actually extended this and exploring more ways of implementing and these filters. You see, this is the first simplification that was made. And what is the benefit? The benefit is that you have reduced the number of storage element, which is a big deal. And we also know that instead of this, we sometimes want to draw signal flow graph. In signal flow graph, a multiplier is shown with an arrow, and we put the A1 here with an arrow, and we put A2 here with an arrow, we put B0 here with an arrow, B2 here, and delays are represented by Z inverse. So you can redraw this. There is a slight difference of notation in terms of the book uses A1, A2 instead of minus A1, A2, but it does not really matter. It's just what you call in A1 and A2 is more, and wherever two arrows are meeting, it automatically means an adder. So the book prefers us to draw signal flow graph. So instead of drawing the boxes and the multipliers, just draw arrows, and wherever two arrows meet, it means an adder. We need not to put an adder there. So this is our signal flow graph IIR direct form 2. So this is direct form 2 representation of filters, and I hope that you understand in direct form as help us to reduce the storage. Okay, but people did not like in the direct form one thing. What they did not like, that here once they were alive and one piece like this, okay, like this, once they were one piece, they were doing the feed forward path first, okay, feed forward path first, and then they were doing the feedback path. Okay, here they are doing the feedback path first, okay, and then the feed forward path. So people want to perform. Why? Because once you are doing a feedback path, your number of bits increases and more sensitive to these coefficients. So now they started thinking that, oh, is there any way I can actually bring my B's on one side and A's on the other side, so they came up with another transformation which is called transposed direct form transformation. And transposed direct form transformation is a transformation where you do the transformation. And now the question is, how do you do the transformation? Okay, so the transformation is that let's say first do the transformation on direct form 1, then do the transformation on direct form 2. Transformation says that reverse all the arrows, and make input once you reverse the arrows, obviously the input will become the output. So reverse the arrow, it is going here, reverse the arrow is going up, reverse the arrow is going up, reverse the arrow is going this way, reverse the arrow is going this way, reverse the arrow is going down, reverse the arrow is going down, reverse the arrow, reverse the arrow, reverse the arrow, reverse the arrow. Very simple. It says reverse all the arrows in an implementation. So the mathematical realization will not change. Okay, the maths will remain the same. Still, it will be the same filter, but it has a very different consequence in its implementation. Reversing the arrow will have a very different connotation. So let's say because I have done this for the direct form 2. So if you do this to direct form 2, it is called transposed direct form 2. It is called transposed direct form 2. So it has become a transposed direct form 2, or which is called TDF. Okay, transposed direct form 2. So what have we done? That we have reversed all the arrows. So this is where I have reversed all the arrows. Okay, let me draw this here with reversed arrows. Nothing else will change. This will still be Z inverse. This will still be Z inverse. This will still be A1. This will still be A2. This will still be B0. This will still be B1. This will still be B2. And this arrow is now like this. This arrow is now like this. But only position of input and output will change. Okay. And as you can see, now you are actually implementing the feedback, feed forward path first, and then you are implementing the feedback path. But we are used to draw x of n on this side. So I have tried, if you are able to see this. Yeah, you can see this. Okay. So you can draw x of n means you take its image. So I'm taking this image by just doing this and drawing this so that you can also visualize. So I am just taking the image, reverse image of this, so that input appears on the left and output appears on the right, and it gives you input. Okay, so this is B0, B1, B2, A1, A2, Z inverse, Z inverse. Okay, and if I put it into the form which we are used to see, a multiplier, a multiplier, a multiplier, a register, an adder, a multiplier, a multiplier, an adder, an adder. Wow. Wow. You see, this is a transpose. This is a transpose direct form 2. Very, very important direct form which is used a lot in implementation. And if you look at this form, okay, here is a register. You cannot directly write a difference equation. Okay, you cannot write a difference equation because of the reason that now it is x of n which is being multiplied with b0, x of n which is being multiplied by x of n, it is b. So x of n multiplied by b0, x of n multiplied by b1, x of n multiplied by b2. Okay, but you know, in our difference equation, b naught multiplied by x of n, b1 multiplied by x of n minus 1, b2 multiplied by x of n minus 2. It has changed the format, but it is still consistent. That is important, that it still implements the same difference equation. By some mathematical rigor, you can come to the expression and you say, oh wow, this is the same difference equation that we said that in signal processing our life is limited to only implementation of this or implementation of this. This is whole scope of my, at least the part of signal processing I have studied, and once I say implementation, this is my life. I have to just implement this simple equation, and anybody who's a programmer can expand it, knowing that every time he gets an input, he needs to implement this, he can update his variables and go through this. But if you have learned signal processing, you say, no, let me explore other architectures. So you explore the first architecture, which is the direct form 1 architecture. Then you explore direct form 2 architecture. Then you explore transpose direct form 2 architecture. And in transpose direct form 2, and you will study this in more detail in our digital system design class, where you will see that this you will implement on FPGAs, but inshallah in this course we'll have you implement these on a digital signal processor, and so that you start appreciating that same equation can be implemented in 4 different ways. And same is the case with direct form 2 implementation, the direct form 1. So primarily there are 4 implementations: direct form 1, direct form 2, transpose direct form 1, transpose direct form 2. Okay, so a typical question in the exam will look like this. A typical example: you may get a transfer function. Dr. Ali has solved some of these, and you say this is the transfer function: 1 plus 0.2 z inverse plus 0.4 z minus 2, 1 minus 0.6 z inverse plus 0.9 z minus 2. Okay, and it may have like higher order, but this is a second order transfer function. And you may be asked to implement this using direct form 1, direct form 2, transpose direct form 1, transpose direct form 2. Okay, you may be asked these questions. So though you can directly start from here, if it is an open book, open notes exam, just use the pen and say this is B0, this is B1, this is B2, this is A1, and this is A2. Okay, so you can say that actually it is minus A1, minus A2. It goes on this, and it's come on the other side as plus A1, plus A2. So it depends that which notation are you using, and just take this from your this, and quickly write B0, put 1 here, B1 put 0.2 here, B2 put 0.4 here, this is 1, A1, minus A1 is minus 0.6, and 0.6, put 0.6 here, and put minus 0.9 here. Okay, this is quick and a quick way of actually solving a question in the exam. That given a transfer function, find out from the book or the notes or the cheat sheet you have drawn, and just put numbers. Okay, if it is direct form 1, and you have seen direct form 1, so you have the direct form 1 architecture as well. So you can do from the direct form 1, direct form 2, direct form 3, any form you have, you can just easily do this. Or the second method is go through the lengthy process, convert this into direct form 1, then cut them into 2, put them here and here, direct form 2, and then change all the arrows, input to output, transpose direct form 1, and do the transpose direct form 2. So a question in the exam can be easily solved if you have an equation and if you have the appropriate direct form. So let me just run you through a few slides so that you know, and you will also find out what is the benefit. Okay, somebody should have asked this question. So what is the benefit of, though I've told you one, but then there are other benefits as well, that why to worry about a simple equation, why to go through all these crazy steps of implementing it in so many different forms. And we will shortly know that, and you will be amazed to know that how many the devil say it is in the details. So we will know that too. So is primarily we know that direct form is the structures or the implementations can be represented in block diagrams form or signal flow form. So there are many possible implementations, and these implementations are direct form, cascade form, parallel form, transpose form, and we have not covered cascade and parallel form at this point. I will cover it in the next lecture. And all you are doing is you are just implementing a difference equation which looks like this. Okay, you see there is a positive A, and sometimes we write negative A and assume all A's are positive on this side. So these are the two different notations which are MATLAB assumes all A's on left hand side, book assumes all the A's on the other side. Okay, so there's only a sign change once you are going from MATLAB to the book notation, otherwise nothing changes. So this is the difference equation, and this is the transfer function. This is the pole zeros plot. We don't implement this at this point. We are not worrying about this. Okay, we'll shortly we come to this expression, but this I've shown you that this is the expression which you worry about, and you assume this as two systems. One is your all poles, and the other one is your zeros. This is the feed forward, this is the feedback form. Okay, so you implement it in two. First you usually implement the feed forward, which is b kxn minus k's, and add them up to get an answer, and then you take this answer and implement the other part. This is direct form 1, which Dr. Ali has covered, that you have an x of n minus 1, x of n minus x of n minus 1. You do the multiplications, add them together. This is vn, and you yn, then you do all the previous samples, add them up together to get y of n. This is by looking at the expression, you can actually develop this structure or implementation. Okay, this is the same example, just a single coefficient, this equation which has only b0 and b1. So b0 and b1 and only a1, so the a1. So and then we have studied that instead of block diagrams you implement flow graphs. So flow graphs can also be drawn like this, where the two arrows meet, it means an adder. On an arrow you write z inverse, it means it's a register, a delay element, or a storage, or if there is a constant, it means it's a multiplier. So this is just convenience, though I don't like the flow graphs because I want to see adders and multipliers because they gives you a good feeling of an architecture. So I prefer drawing the adders and multipliers and registers to see what actually is going to happen if I implement this on an FPGA. But this flow graph form is good because using this you can easily convert it into the transpose form. So this is the same signal flow graph for direct form 1. There are registers, B's, y of n, previous values of y of n, multipliers, and as I mentioned in the exam, if you have drawn this and you are given a transfer function, all you need to figure out your b0, b1, b2, and a1, a2, a3, and just instead of write rub this, and just put the values constant, and you are done with the answer. So you don't need to get into detail because you can just do the answers. So multiple structures are, we have already seen that basically resources that you are reducing number of delays and sometimes adders and multipliers. But one thing we will see that why people are more cautious about these architectures are because of the, especially for IER filters, their stability, and the robustness of the stability, the overflows, the error propagation, the quantization. It's very, very complex subject to actually understand what these different structures are going to do to your signal. It's not a simple subject. It's a bit complex because now then it gets into stochastic and the error propagations and all that type of stuff. But you must have an understanding. So no matter once you go and you do a job that relates to whether it is digital communication, signal processing, pattern recognition, and you are actually implementing systems on machines, and maybe on developing interesting architecture, and that what I see a computer engineering is about, that you are developing interesting architecture for algorithms and or implementing these on embedded systems. And so this is what these and direct form 2 we have seen is very simple, that you cut it into two parts, move this here, move this on the other side. This is what we have done. And so this part is appearing here, this part is appearing here, then we see all these delays are common. So we basically, once these delays are common, then we merge them together and reduce the number of delays. And then we realized that, oh, this is a good form, but now I am implementing the feedback part first. And then I am implementing the feed forward, and I sometimes hate to do this. I want my feed forward part to be implemented, which is simple to implement. I want to do that first, and then I want to deal with the feedback part. So that primarily, so this is in the block form that these delays are common. So you merge them together to get these delays. And then are the this is the example I have done. The same thing. I told you that if you're doing an example, put the transfer function in this form. You may not even need to write the difference equation. Just write this is b0, b1, b2, and with the negative sign and the bracket, this is a1 and a2, and just go and put these numbers there, and you're done with the question. So this should be the simplest to get marks, the question in the exam. And somebody, if somebody cannot solve this, it's very bad, because it's only looking at these numbers and filling them on any of the architecture you have. Especially we allow you to have an open book exam or an exam with a cheat sheet. So this is we will come back to the quantization and the studies, and interesting studies, that what happens to your stability of the system, error propagation. This we are going to see, inshallah, the cascade and the parallel form. But we started today the transpose form, and we said transpose is simple, that you change the arrows to these arrows are changed. So you change the arrows to the other arrows. Okay, so change the arrows, and once the arrows are changed, you get this, and then you flip to see it has already been you flip so that the input is on the left hand side, output is on the right hand side, and you get an architecture. This is the transpose direct form 1. We are not really interested in transpose direct form 1. We are mainly interested in transpose direct form 2. This is the form which the MATLAB default form is. Once you design a filter, MATLAB default form is transpose direct form 2, cascade transpose direct form 2. And we will see once we design this filter in MATLAB. I'll show you that this is what the MATLAB does. So this is what the MATLAB does. You have interesting form where you have less number of registers, and your input doing the feed forward first, then you are doing the feedback. So this is, if you have any question, I'll be happy to answer that question. So we have like 7 minutes, and ask questions, or I will solve maybe another example for you otherwise. So let me solve you a question. I hope this is simple, right? I don't think so. It is, let the same question, let it be the same question. So if I ask you sometimes to write a difference equation for this, so you can easily write difference equation. Y of n is equal to, so this is will go on the other side, it will become 0.6 y of n minus 1 minus 0.9 y of n minus 2 plus x of n plus 0.2 x of n minus 1 plus 0.4 x of n minus 2. Okay, so this is the difference equation. If asked write the difference equation, you can write the difference equation. And now I say put it in all the 4 forms: direct form 1, direct form 2, direct form 3, and in block diagram, or maybe the signal flow graph. So direct form 1, looking at the equation. So let's say you don't have notes and where you have drawn these. Looking at this, you can draw, yes, you can draw this. You say this is my x of n. X of n multiplied by 1. So you need not to have a multiplier even. I put a register, here I get xn minus 2. So I put another register, I multiplied 0.2. I multiplied by 0.4, and you also label it. Sorry, n minus 1. Okay, and then you say I need to add this. I need to add this here. So this being added here, this is the adder, and then this all is added in x of n, this is the adder. So you do this, then you have y of n this is a1, which is 0.6, and this is minus 0.9. This is direct form 1. In direct form 2, you take this part and make it here, and take this part, make it here. Okay. So xn will remain here, yn will remain here as you cut. So you have x of n, you have this adder, then you have this adder, then you have this, then you have this arrow, then you have this multiplier, then you have this multiplier. Okay, then these two registers. So because they are going, and then this part here, registers are the same. So you have this multiplier, which is with 1, you have this multiplier, which is 0.2, you have this multiplier, which is 0.4. Then you have adder, this adder, this adder, and there is no adder here. This is direct form 2. This is direct form 1. And then is the transpose. Transpose direct forms are where you only need to change the direction of these. So let's change their direction using a red pen. So change the direction. Change the direction of arrows. Arrow, arrow, arrow change, arrow. So this is change, this is change, this is change. Okay, it was going down, this is now going up, going up. So you change, sorry, it was going up, so it is going down now, going down now, going down now. So this is a direct form 2. I don't mind even if you yn becomes xn, xn becomes. So if you even draw it like this, it is okay. Okay, but usually you draw the input on the left and output on the right. It does not really make any difference otherwise. And similarly, for this also, you inverse all the arrows. So this arrow will now be this, it becomes x of n. This arrow will be this will become y of n. This arrow will be like this. Here it will be like this. This arrow will be down, down. This arrow will be here. 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 So this is transpose direct form. So you can draw transpose direct forms like this. So this really brings me to the end of today's lecture, where we have seen interesting ways of implementing. Still we have a little appreciation of why we have all these different architectures, and I hope in our next class we will get more appreciation of these different implementations. And once you study the next course, which is digital system design, you will even have more insight into why these are so differently implemented. Thank you very much. And please try to solve the quiz I gave you. It's a question from the exam, and I hope that without consulting anybody, and I'll urge you not to consult each other. Okay, just try, read the book, go listen the lecture again, read the book, go listen the lecture again, and try to grasp the essence of linear phase filters, and the knowledge that a zero means 4 zeros, and type 3 means that 2 additional zeros, one at 1 and the other one is at -1. Thank you very much. Inshallah, see you next time. Apna khayal rakhiyega. Khuda Hafiz.